Hello and welcome to this webinar on condition monitoring for maintaining asset health. My name is Jason Tranter and I am the CEO and founder of Mobius Institute. So I have been involved in this industry of vibration analysis, condition monitoring and reliability improvement since about 1984, a long time ago. And I tell you that because over all of those years I've seen a lot of successful programs and a lot of programs that haven't had that much success. I've seen programs get started and then after a period of time, for a variety of reasons, kind of fall back and maybe even stop altogether, and then maybe later starting up again. I've seen also a lot of programs that utilize the technology of condition monitoring but don't really take full benefit and don't get the full value out of condition monitoring, because at one extreme you can use condition monitoring just to tell you that there is another problem, but often those problems are avoidable, and the question is, are you taking full advantage and avoiding the problems, not just detecting them so we can manage the problems? So that's kind of the emphasis of this program. Okay, what are the condition monitoring technologies and how can we take full advantage of them to move towards reliability improvement? Just so you know where we're coming from, were founded in 1999 and we provide training in vibration analysis, condition monitoring and reliability improvement. We do that all over the world. We've got training centers in almost 60 countries. We train in about 90 countries all told. We've trained thousands of people every year, in fact. And we have certification which is accredited to the standard you can see there, ISO 17024, which means we're audited and all that sort of stuff. So we have e-learning, classroom training, lots of good stuff. So that's our thing. And as you can see, we're all over the world. So let's get started. We all know that reactive maintenance is costly, it's dangerous, and it's harmful. It can cause or result in injury and environmental damage. It can cost the company dearly, both in terms of the much higher maintenance costs, but also just the fact that you're not producing or providing the service that you should. And particularly when it gets into a manufacturing environment, and particularly a discrete manufacturing environment, all those breakdowns, slowdowns, i.e. reduction in throughput, and poor quality cost the organization dearly, and we can do something about all of those issues with condition monitoring, but especially when you get into reliability improvement. So the big question is, why does it happen? Why do we have those slowdowns, breakdowns, the higher maintenance costs and everything else? Because it can be so frustrating. It can be frustrating from a business point of view that you're unable to satisfy customer needs. It can be frustrating from a production point of view that you're not meeting your targets and you're dealing with problems all day long. And it can sure be frustrating from a maintenance point of view, dealing with constant problems, constant breakdowns that we have to repair this problem and deal with that problem and deal with the next problem. You really would like to get on top of everything. So just for a bit of fun, I like to depict the situation from a maintenance point of view with this whack-a-mole game. So there's the poor maintenance person who may have full intentions to be proactive in the maintenance tasks, do things with precision, deal with problems early so that they don't cause more problem later. But every time you deal with one problem, another one pops its head up, and then another problem pops its head up, and you're constantly just trying to keep up with all of that. So along come people like me and say, well, you should do things that are proactive, and oh, you should do this and you should do that. And they say, well, that'd be great if only I could break out of this cycle. Now, if we were to look at what's happening inside here that's causing all these problems to come up, Now, we won't go into a lot of detail here. All these little the moles that keep popping up, they're kind of like lemmings that walk to the edge of the cliff and fall off. But some of them are age-related. You see, some of them are getting old. Some of them are what's called infant mortality, that we fix something and it immediately breaks again. Some of them just fail randomly. In fact, a lot do fail randomly. So without going into all of that, what's feeding all these problems? What's happening back there? And unfortunately, what's happening is that as part of the design process, the procurement process, all the engineering that goes on, and the maintenance processes and practices, the way we manage the spares, both what we keep and how we store them, the way we operate the equipment is a big source of problem. And yep, some things just after a period of time will fail, and then we get all these random failures. And this cycle just keeps continuing and continuing. You know, if we don't design for reliability and maintainability and operability, if we choose the cheapest spares and components to be used, you know, we're just going to keep, you know, going around and around with this cycle of experiencing problems. Now, condition monitoring can help in this situation. So the condition monitoring person can say, I can see a problem coming, and warn the maintenance person. But he'll then see, he or she will see another problem coming. Oh, maintenance, hey, there's a problem coming here, great. Hey, maintenance, there's a problem coming here. Oh, great, I can deal with that. But the trouble is, there's all the breakdowns that are happening every day again. So condition monitoring helps, and it can reduce our costs, and it can certainly reduce the risk of unexpected failures. So it is a good thing. It is absolutely a good thing, but we need to go further. Because what if we went back and we said, hey, design department, look after that equipment. Let's reduce the cost of ownership, the total cost of ownership, or our life cycle costs. If we made better decisions with what we purchase, if we managed our spares better, if we operated the machines smooth, happy, consistent, looked at changeover issues and shift changeovers and all of that sort of thing. So it's not to say there won't be problems. Some problems do come up because there's wear out and so on. And it's unrealistic to think there'll never be problems again. But boy, when we have the right focus and the right activities, we can reduce the source of all those problems, and then maintenance has the time to do the precision work and the proactive work and everything else. So at the end of it all, condition monitoring, working with operations and maintenance, we can not only detect problems and alert maintenance and alert operations so they can say, okay, well, this is the best time to do the work, but we can also detect the signs that result in failure coming. So we can see the root causes of the failures and say, hey, if we don't do anything, this will cause failure. And then condition monitoring can warn you and maintenance can do something about it. But we'd rather detect problems really before maintenance had to get involved in that sort of repair action. We'd rather just take steps to avoid the future failures. So the good news is, particularly with rotating machinery, but it applies to all machinery, we are warned in lots of ways. As those rolling elements roll along inside the bearings, we can tell if there are cracks, spalls, lubrication issues, installation issues, if there's electric current flowing through, all sorts of things. And with gears and timing gears and belts and lots of other sorts of components, we can see if there's wear, cracks, balls, if they're misaligned, overloaded, and that goes for all sorts of components. We get lots of warning about these problems. And we can, for example, detect temperature changes. So we can use our infrared cameras and other tools, but we can see the signs of changes in temperature. So we can see electrical problems, mechanical problems, issues with flow, what's happening in tanks, what's happening with steam traps, all sorts of things by measuring temperature. With our electric motors, we can tell if there are supply problems to the motor, like voltage with harmonics. We can see imbalances in voltage across the three phases. We can see if there's problems with the connectors, with the stator, with the rotor, broken rotor bars, insulation issues. Boy, there's all sorts of tests we can perform on our critical and precious electric motors. Lubrication is such an important key to successful reliability improvement. So here, if we got down at the microscopic level, both where the gears mesh together and where the rolling elements roll along the raceways and so on, we're getting down to the micron level. That's 1/1,000,000th of a meter. And the lubricant performs such a critical role, whether it's oil or grease. It keeps those rough surfaces apart. Yes, they're rough at that microscopic level. So it plays an important role, but boy, if it's contaminated with particles or water or glycol or anything else, it will cause failure. So we need to avoid it. It's as simple as that. And the lubricant itself is precious and expensive. It's precious to purchase. It's expensive to dispose of. So we can use condition monitoring to see if the lubricant itself is able to do a good job and whether it needs to be replaced. For example, just having a tiny little particle there in the oil gets in between the rolling element and the raceway and causes a tiny indentation. Now, this particle might be 4 microns in size. It's tiny. You can't possibly see it or feel it if you rub the oil on your fingers or the grease, but it causes a tiny indentation. But as those rolling elements keep rolling by, that little tiny indentation there will turn into a spall and will result in failure. So, if we can avoid contaminating the lubricant, that's really important. If we can perform tests to see that the lubricant is contaminated, then that's really important. We can use ultrasound to get an early warning of lubrication problems, to detect the signs of bearing wear. We can find all kinds of mechanical faults, electrical faults, flow-related faults, all sorts of things. Anytime there's any impacting, friction, turbulence, it generates very high frequency vibration, or sound if you even like, and we can pick it up with ultrasound. We can even listen to the bearing while we are greasing the bearing, and as the surfaces move apart, we can hear the difference. Now, we never want it to be like that, even like that. But we can hear when we've put in the correct amount of lubricant, and that's when we should stop. We shouldn't just keep pumping grease in. We'll hear the difference if we do pump in too much grease, but that we don't want to do. And then we've got vibration analysis. We can put a vibration sensor on the machine and it will measure the up and down, the vertical vibration. Now, machines vibrate in 3 axes, so we also measure horizontally and axially along the length of the machine. It just depends if there's an unbalanced problem, a misalignment problem, a problem with the bearings, and so on. There's different places we take our measurements, and we can learn so much from even just an overall level, just a single number that represents the vibration. But gee, if we look at the spectrum, the time waveform, phase measurements, there's so much we can learn. And just as I'm showing that transparent, it's almost like the vibration takes away the cover of the machine, and we can see what's happening with the bearings and the rotor bars and the shaft as it turns around. Is there cavitation? Is there a problem with the bearings? Vibration analysis boils it down to the individual frequencies that tell us there's a problem. So that's all great, and we can apply it to piping, valves, transformers, heat exchangers, switch gear. So much equipment. It just depends on the equipment and the failure modes that all enable us to tell exactly what's going on with the machine. So one way to look at the way condition monitoring works is with this curve, sometimes called a PF curve. But the basic idea is, here's the passage of time. Here's our machine running, in time, and it's indicating that right now it has good condition. So the condition is good, and it's supposed to operate that way. And if it would only just keep operating that way, we would all be happy. The machines would just keep running, we would achieve our production targets, the service we provide, say wastewater treatment or something, would be dependable, all good. But for a whole variety of reasons, a defect is eliminated. The machine might be misaligned, or that contamination is occurring, and a little while after that we can detect that failure has started, and we call that the P in the PF interval. So there's P for potential failure. And then it all depends on the failure mode, as we call it. How much time is there between us being able to detect the problem and the machine functionally failing. Now that doesn't mean that it's catastrophically failed. That just means, hey, we have to replace it now. We have to do something because it's no longer able to perform its function. But if I could detect it way back here, that would allow us to plan and schedule the work. So as I say, depending on the failure mode, this could be a matter of minutes in some extreme cases, or even seconds, or it could even be 1 year. And it's all going to depend which failure mode it is as to whether we can hear it first, measure it in the oil, or whatever. But usually, particularly for mechanical problems, the bearing getting hot and making sound and so on, that's very late stage. That's almost days to failure, and at best weeks to failure. But anyway, if we can pick it up early, we can order the spares, plan the job, make sure we've got the right person with the right tools and the right parts and skills and everything else ready to do the job at the appropriate time. And the scheduler works with operations and says, okay, this is going to be the best time to do the job, so the job gets done. And we reduce the cost and we reduce risk. But when we're detecting at really late stage because someone says, my goodness, that bearing's making an awful sound, we're really on the back foot at that stage. It's going to cost us a lot more, and we're taking a lot more risk. So with condition monitoring, what we've just described is great. We're detecting the fault, and therefore we can deal with it. We can plan the maintenance, we can avoid secondary damage. So for example, if the bearing fails, rather than just replacing the bearing, we might have to replace the whole shaft or component and seals, and there's a ripple effect when something fails like that. We can reduce spares inventory, because if we know we're going to be warned about certain failures, then we can just order the parts when we need them, which saves the company a lot of money. There can be fewer safety incidents and environmental incidents. But the big question is this really reliability improvement? Have we really improved reliability? Like, particularly when we look at each individual motor, pump, fan, compressor, or whatever it is still failing as frequently. In fact, pure condition monitoring is kind of like reactive maintenance. It's just that we're reacting a little earlier. And so a lot of people say, hey, I've got a reliability improvement program because I do condition monitoring. Now if you step back further, yes, the production process or the service is more reliable or is more dependable because we're managing the failure. That's the thing. We're really just managing the failure. We're not avoiding the failure. We're just saying, okay, failure is going to occur. Condition monitoring gives us an early warning, and that's good, but we'd really like to avoid the failure in the first place. So the question is, why do our assets, why does our equipment fail? And it's an awful thing to say, but it's because we kill them. If we don't keep the machines precision balanced, then as the shaft turns, it rocks when it's overhung like this. It tries to move up and down in this sort of, because of the centrifugal forces, and these bearings just don't like that. The extra load on the bearings drastically reduces their life. The whole structure doesn't like it, and we can have cracking and failure. The vibration can get into other machines. The vibration can excite things called resonances. It can affect the coupling and the motor itself. So it's not good. With misalignment, okay, all my animations exaggerate the motion so you can see it. But this is what's happening, when it's just a little bit of offset or parallel misalignment, the couplings, the shaft, the seals, the bearings, what's happening inside the motor there and the pump with the available clearances, it's not good for the machine. And all that vibration also transmits down into the base and the foundations, and it can harm that as well. If the bearing isn't installed properly and it's just cocked on the shaft, then that will reduce life as well. If the bearing was cocked in the housing or there was angular misalignment, that puts all sorts of extra load on these rolling elements. Even if it's just cocked by a little bit, it reduces the life of the machine. When these rolling elements roll along, it applies a lot of force on the rolling element itself and the raceway, and my animation shows it sort of flexing as it goes by, and it really does do that. Maybe not to the extent that I'm showing it here, but so that you can see it. Now that's the way the bearing's designed, and it can cope with a certain amount of load. But when there's too much load, because of the way it's operated, balanced, aligned, installed, all these other things, we can get fracturing under the surface, and it cracks and cracks and cracks and cracks and finally comes through to the surface. Now, vibration analysis, for example, can detect when it's starting to fracture underneath the surface, and then when it breaks through to the surface, other techniques will detect it, and certainly when the pieces of metal fall away, then we might detect it in the oil sample and so on. But again, we just need to keep the load per the design, and then that doesn't happen. I've already shown you, what happens when there's contamination. It's very harmful to the machine. Instead of being sort of rolled over, creating indentation, sometimes those little particles can sort of skid along in front of the rolling element, and it sort of scores the surface. It damages the surface, which I hope you can see there. And we can have a situation where there's current passing through the rolling elements. Now this is common with DC drives, but also with variable frequency drives, and that also damages the surface of the bearings and gears for that matter. When you've got a unit in standby mode, its mate next to it is vibrating because it's operating, and therefore this machine will also sit there and vibrate. But because the rolling elements aren't turning, it creates these indentations, and that happens when bearings are being transported. It happens when bearings are sitting on the shelf as well. So there are ways around all these problems. If we operated this machine more frequently, or if we mechanically isolated the machines, we can solve these problems. No worries about that. So if for any reason the bearing is damaged, whether it's a crack like that or anything else, the vibration and the ultrasound will change, and we can detect it, we can see the resonance, we get these shock waves, all sorts of things. That's all great. That's just terrific. But what condition monitoring can't do is that. It can't fix the bearing. It just tells you, sorry fellas, there's another problem. There's another problem we have to deal with. And so that's not good. So condition monitoring is great, but we need to eliminate all the root causes of those problems and all the other root causes that exist, and there's lots more than what I just described there. But it's also true that we need to go beyond maintenance to improve reliability. Everyone points the fingers at maintenance. Oh, if you guys only did your job properly, and if you wouldn't keep messing up the machines, and it's like, no, wait, yes, maintenance will influence reliability. Absolutely. But the way we operate the equipment and the design process and procurement process, all the stuff we saw before in the whack-a-mole game, that has to be taken care of too. It's not maintenance's fault. And if you create a reliability group, it's not their fault either. It's not their sole responsibility to improve reliability. I see that a lot, and it's just the wrong approach. So here is that PF curve we saw before. Condition monitoring sort of operates in this space normally. What we need to do is look earlier. Use our condition monitoring skills to detect all of these reasons for rotating machinery for the problem. So because of this, we see that. But what if we detected this and eliminated it, when the opportunity arises? I'm not saying, oh, there's a slight unbalance, let's stop the plant so we can balance that machine. But when the opportunity arises because some other repair's being done or there's another shutdown or whatever, we go ahead and we make sure we eliminate those problems. But what we also do from a maintenance point of view, okay, I'm going to be pointing the finger at maintenance for a little while, but hey, when we do couple a motor to a pump, we precision align it, we eliminate resonance, we eliminate contamination, we do precision balancing and all those things. So yes, we need to detect it with condition monitoring, but we need to do the best job we can. And if we go earlier in time, the last time the machine failed, was the repair work done with precision? Was it properly planned and scheduled? Did we go through the proper commissioning process to start that machine back up again? How were we operating the equipment? And as always, what was the maintenance like before then? But if we go back further in time, all the way back to the start, now you can't do anything about the beginning of life for your existing equipment, but you can sure influence everything you do from now on, whether it's purchasing replacement pumps and gearboxes and whatever, or if you're expanding the plant, or whatever you're doing. We need to look very carefully at our strategy, at the design process, procurement process, and so on. As I've already mentioned, our priority needs to be the life cycle costs, not the purchase costs. Now, some of you may be listening to that and saying, oh, absolutely, I believe it, but management don't see things that way. Well, that's the problem with the Reliability Improvement Initiative, to be honest. I've spoken a lot about technical issues, but it's all about the people. It's about the people in the work they perform, the decisions they make. It starts from the most senior management all the way to the person who operates the equipment, maintains the equipment, and so on. Everyone needs to understand the importance of reliability improvement. Most people seem to understand safety, and it's obvious. If we don't, there'll be injuries, and that's bad, and there's costs associated with that as well, and regulatory issues. But hey, we don't want injuries, and we certainly don't want deaths. But we need that same sort of thought process when it comes to reliability. We don't want these problems to occur later. We'd rather achieve our targets, achieve our goals, remove the frustration, take pride in our work. But senior management need to understand that and make decisions accordingly. I will spend a little more here so I don't get those problems later. I am going to perform acceptance testing to check everything that gets into our plant to make sure it's going to give us good, reliable service. Because if we do that and then we go forward in time again and we're operating the equipment with good condition, and we're operating the equipment with good condition, and we keep going forward in time, and what happened to that PF interval curve? Yeah, it's not there now because the machine just keeps running and running and running. Now, it's unrealistic to think that there'll never be failure, and we need to keep doing condition monitoring. It's going to happen. It's just not going to happen 2 days after you start the machine, or 2 weeks, or 2 months, and maybe not even 2 years. It could be a long way down the track when these faults occur. It just all depends on a lot of things, the failure modes, the equipment, but still all of those root causes that lead to failure. So another way of looking at it is, there is our precious machine. I've got it sitting on a pillow there. It's performing a critical function. We need to put the force field around the plant and say, no, we're not working with suppliers that provide equipment that turns out to be unreliable. We don't want to be purchasing cheap spares. We've got to be careful how we transport equipment to the site. We are not going to let unskilled contractors come into our plant and perform work in a haphazard way, and we have to deal with that for a while. And we're not going to, allow for poor designs. So all of these things hopefully stop problems from getting into our plant, but now we have to protect the machines from ourselves. The contaminated lubricant, the damaged parts. And when I say damaged parts, that's because you put them on the shelf, but they sit there and vibrate and they're exposed to humidity and dust, and then we put them into the machine, but they're already damaged. It may not have been the installation process or anything else. You're putting in faulty equipment. It happens all the time. All the time. The way we install and the way we operate the equipment and performing unnecessary PMs, boy, that's a big one, and performing intrusive inspections. So, we are protected from the outside world, and we're taking precautions to protect ourselves as well, and that's stopping all these problems. We just deflect them. It's like, no, they're not going to happen. They're not going to affect our machine. And then we keep the equipment clean, we make adjustments, we replenish the lubricants and fluids and so on, and we monitor it to make sure it's all good. And it is happy. We're monitoring it, and it does what we want it to do. And if we don't do those things, then the reality. The machine acts like a beast, and it fails at the most inconvenient times. That's our reality. So how do we do all this? How do we achieve all these great changes that I'm talking about? Now, okay, that's a big chart. Oh my goodness, look at all those boxes. What's going on here? So what I want to do is, we call this the roadmap to reliability. And what I want to do is just focus on certain things here. Because right here is where a lot of companies strive to make changes. So we have condition monitoring that just warns us when problems are coming. Condition-based maintenance is actually different. Condition-based maintenance is the situation where we say, well, we are not going to perform maintenance unless the condition indicates that it's necessary. So no more time-based replacement of components when those components are actually perfectly fine. And that means that we will use our condition monitoring technologies, we'll plan our maintenance accordingly, but there'll still be some time-based and production cycle-based maintenance work, and we will identify equipment where we're not even going to take any special precautions, because everything we do has to have a basis in the economics of the situation. Anytime a person takes a measurement or performs any sort of maintenance work or analysis or anything else, it's time, it's money, and it's using resources, if I can put it that way. It's using people's time that they could be using better in other areas. So ultimately, we need to identify, well, where is that appropriate, where is that appropriate, and where is that appropriate? And in some cases, we need to identify equipment. Well, we just need to replace it or redesign it because it's just so much trouble and we can't detect the problems. So how do we do that? Well, we build a master asset list to make sure we actually know what we're dealing with. We look at criticality. There is a real big one, and a lot of people unfortunately don't fully understand what criticality means and come up with something that's a little too simplistic and it doesn't work. But understanding the consequences of failure and the reliability and the detectability, our ability to see the problems coming, enable us to rank the equipment. Because if something ranks very low, we might be able to just run it to failure. Because what that means is that it's either proven to be reliable but the consequences of failure are very low. It's not worth taking the vibration readings and performing some of these other tasks. But knowing that, we can then look at the more critical equipment, and there's where we can justify some of this sort of work. Understanding the failure modes, doing the failure modes effects analysis, assessing the risk and the detectability like I just described, and ultimately developing the strategy that enables us to make these decisions. Now, sometimes people call this RCM. reliability-centered maintenance is performing these tasks. We can also perform reliability studies as well. Let's look at Pareto analysis and maybe look at the mean time between failure. But boy, there's a lot I could say about that particular topic right there. But we do all of that so we know where our problems are coming from. Now, when we do all of that work, that's great, but that's very much focused on maintenance. It's very much about dealing with the problems we have. We haven't really eliminated the root causes of failure necessarily. Now, a more enlightened approach to this will also identify the root causes and create maintenance activities or maintenance tasks and PMs that avoid failure. But we can also step back and say, right, remember the design and procurement comments I made and how we manage spares and the planning and scheduling or work management process, the precision skills that we need to do all of our work, whether it's rotating machinery or anything else, doing that work properly the first time. And the way we operate the equipment and following standard operating procedures, and the maintenance work, remember the lubrication and making the necessary adjustments and preserving the function of the equipment, because all of this is about defect elimination. It's eliminating the root causes of failure that extend the life cycle of the equipment. But none of this is possible unless we deal with the reliability culture. We need strong leadership that believes in this and focuses on it and makes sure we get it right. We need a vision and a strategy. We need to have a plan for all of this, and we need to execute that plan. To do that, we need to understand what's important to the organization. We need to prioritize our work. We need to understand how we create value through this process. We need to understand things like human error and how change management works, and we need to be very good communicators, and we need to constantly communicate. And we sure need to look at training. Now, okay, I run a training company, we provide training, but however you are trained, whether you do internal training or go to someone else, that's not the issue here. The issue is that everybody needs to be educated to some degree. The biggest mistake you can make is say, oh, hey, you reliability engineers, you go and get training so you understand this, and you condition monitoring technicians, you go out and get training on the condition monitoring technologies only, and the people involved with work management and spares management, everyone gets trained in their silo, but no one knows what the next person's doing. No one, these people do not understand the implications of what they do on the planning and scheduling and production process. These people often don't understand, sometimes in the worst cases don't even understand the plant itself. I've seen some interesting situations where they work almost isolated from the equipment. They don't even understand the ramifications of the decisions that they make. But if everyone understood everyone's situation to the necessary level, not everyone has to be an expert vibration analyst or something. It's just that we all need to understand the role we play and how it affects others. But we also have to have the depth of knowledge in our particular field, and we have to have the skills to operate and perform these maintenance tasks properly and choose the right spares and everything else. And then there's the continuous improvement role. We start by analyzing our situation, making an assessment, doing an audit and benchmark if you like, establishing KPIs so we can measure how we're going, and then we use that information to constantly improve what we're doing. We perform root cause failure analysis so that even after all of our work, if we still see failures occurring, we ask the question, why did it happen? What can we do to avoid it? And then we take the necessary steps to avoid it. So all of that's very important. We need a plan that deals with all of these issues. So back to the condition monitoring picture. Condition monitoring, if that's your main environment and all the things I talked about you may feel are outside your scope, well, condition monitoring still has a very important role to play. A very important role. Number one, we're avoiding those catastrophic failures. So that is super important. But number two, we can, in a condition monitoring role, detect the root cause of fault. So we can see, hey, look, this machine's not being operated properly. We've got contamination in the lubricant, all these things. We can do that because, if we look at the fact that there's unbalance or that the installation job wasn't performed correctly, if we have misalignment or soft foot or resonance or turbulence or cavitation or any of these issues, if we can detect those problems, then we can avoid the leaks and contamination and the seal failure and the bearing failure and all the other problems that can come along. But we can then be proactive as well. Now this is maybe starting to get outside our particular area of expertise or influence, but we can make sure we balance to a very high tolerance and aim for G 1.0. Talk to the people who do your balancing and say, can you balance to G 1.0? Can you perform precision alignment and soft foot correction, shaft and belt alignment, precision lubrication, eliminate looseness, which is obviously specific, a lot of these are to rotating machinery, optimize the tightness. I don't know, optimize is the right word, but tightening to the correct tolerance and tightening bolts in the correct sequence, whether that's on a flange, a pipe, or the machine hold down bolts. We need to eliminate resonance. It just amplifies vibration. We need to look at all of our installation practices, and even if the condition monitoring group aren't involved in the installation itself, we can be there immediately afterwards to do a sort of a QA check. Hey, how did it go? Are there any problems before we start operating the equipment for the longer term? And we can get involved in root cause failure analysis. So we can determine the root cause of the equipment, and then a change needs to be made. We need to verify that the change was actually made and that it was effective. But from a condition monitoring point of view, if we look in the oil samples and we see this, well, that's called cutting wear. It looks like something that came out of a lathe, but it's very small. These are very small pieces of metal that are in the oil. And when I see that tells me that there's a certain sort of wear going on inside the machine. Little particles are sort of shearing off slices of metal. I think we even had an animation on that earlier. And so I can see that and say, aha, I know why that occurred. I can, for sure, you should always, particularly on the critical equipment, take the bearings out when you've diagnosed a fault and you do something about it. Take the bearing out, look at the surface. The surface pattern tells a story, and you can tell exactly why the failure occurred. We can see slippage on the rollers, corrosion on the raceways, corrosion when the oil comes out of, when the water comes out of the oil. Sometimes it might seem like the oil's coming out of the water, but it pulls up around the rollers when the machine's standing still, and we get corrosion as a result. There's false Brinelling when the bearing's vibrating when the rolling elements aren't turning. And then we can perform those QA, QC checks that I mentioned during commissioning, but also acceptance testing. We need to say, if it does not meet our standards, it does not get into the plant. And you need to create purchase agreements that say, you will do these tests, they will be verified, they'll be performed in exactly this way, and if they don't meet our standards, then certainly the warranty period does not begin. You look at how the payment process will be affected, but you need good equipment to be installed. But you really have to help create buy-in to this whole process. Senior management need to know the importance of everything we've talked about here. Everyone on the plant floor needs to understand the importance of what we've talked about. Everybody needs to buy into this process. Everybody. As I've said before, I cannot emphasize this enough. You cannot solve these problems with technology alone. No amount of vibration analysis or reliability analysis and all these things will totally solve these problems. There may be a good ROI on performing vibration analysis or whatever. It can be justified for sure, but you won't have the sustained success that you can if you address the reliability culture. It's so important, and that certainly involves making sure everyone has the right knowledge and skills to do their job. So in conclusion, no doubt about it, breakdowns can be so frustrating, absolutely, but there is a solution. We can monitor the equipment, the condition of the equipment, to prevent the failure. We can improve safety and the impact on the environment, and we can plan future maintenance. Hey, that is great right there, absolutely. But if we eliminate the root causes of failure within the plant, and then we achieve the contribution of everyone in the plant, that's when we'll have success. And I didn't emphasize this enough during this presentation. It's not just about having people believe in reliability improvement, it's having everyone contribute to it. People always say, people don't want to change. Everyone's so resistant to change. But I would like to put just a different spin on it. I didn't invent this stuff, but I put a different spin on it. People don't like to be changed, but they are all fine with change if they know what the benefits will be and they get to contribute to the change. If I said to you, I want you to change in this way, you might cross your arms in front of you and say, what do you mean you want me to change? Does that mean everything I've done so far is wrong? You're blaming everything on me. Why do I have to change? And what's the logic in what you want me to do? And then, of course, they'll think, well, why didn't you ask my opinion? When you talk to maintenance technicians and people who operate the equipment, hey, they know so much about the reasons why equipment fails, why we have quality issues, slowdowns, minor stoppages and so on. They know so much about that. If you engage with them and ask them their opinion and get them involved in the improvement process, can you imagine the difference between just telling someone they have to do something different versus asking their opinion and actually asking them to be involved with or take complete control of the changes or the ideas that come up? How are people going to feel? How much pride are they going to take in their work? Is this going to be just another flavor of the month, or is this people actually feeling good about what they're doing? Without taking too much time on this, survey after survey shows that what motivates people is not money and that sort of material side. Everyone needs to earn a certain amount and they don't want to be shortchanged or anything. It's important, but everyone, including you listening to this, surely knows that you'd rather have job satisfaction. You'd like to know that you're respected in your work, that you get to do your job properly, that you're part of something important and you're contributing to that. And we can do that with reliability. We can, it's a reliable plant is a safer plant, it's an environmentally responsible plant, and it's a competitive plant that stays open. And everyone needs to consider that issue. How competitive are we, either with sister plants or imported products or whatever it is? And we need to be doing everything we can to get our job satisfaction, but to add value so that the doors stay open. Anyway, so if we do that, we'll all just be happy, happy, happy. Wouldn't that be good? So, thank you very much for listening to this presentation. I hope you've found it useful. Again, my name is Jason Tranter, the founder and CEO of Mobius, and we provide all sorts of training and certification, and we have conferences and a website with lots of good information and all of that. But I really hope this presentation has helped you in what you do in your daily job.